Okay, let me try it again. All right, so welcome to a Compass seminar. Today presenter is Dr. Xianglin Ren. Xianglin got her bachelor degree from Ocean University in China. Graduated in June 2020, which was not the easiest time for everybody, right? And then she started her PhD studies at the University of California at Riverside. Graduated with PhD in 2025, and then moved to Rosenstiel to work on a project centered on Agulhas return current and its importance in climate. I asked Xianglin a couple of silly questions. The first one, what she likes about Miami. She told me that she enjoys scuba diving and warm weather. And I asked her what she hates about Miami, and she told me, well, she likes everything. I asked her, how about traffic? Everybody complains about traffic. Xianglin said, well, it's still better than LA, so I guess you are a happy person here, right? Okay, so Xianglin will talk about driving mechanisms of global marine heat waves in a warming climate.
Okay, thanks Igor, it's a great introduction. Today, so I will talk about the research that I conducted during my 5 years PhD in the UC Riverside. And I think marine heat wave is a major part of my PhD research. And also this is my thesis work. So, okay, let's get started. So before we talk about why marine heat wave occur and how the driving mechanism it is, so we first need to define what they are. A marine heat wave is a discrete, prolonged, anomalously warm water event in a particular location. And so if we want to detect a marine heat wave event, so usually, so first we need to have a SST data and daily SST output usually. And so we have three criteria to detect the marine heat wave events. First, so the SST should above the threshold, and the threshold is usually will defined as a 19th percentile of the daily climatology. And then, so when the SST is over the threshold, so it needs at least 5 continuous days, and there should no less than 3 days interval. So we can define this red part as a marine heat wave events. And we usually describe marine heat wave by 3 different metrics, like the duration, how long this event lasts for, and frequency. Here I use the annual average frequency. The average number of the event happens per year, and also the intensity. So here I use the peak intensity, which is the maximum temperature anomalies. And so marine heat waves are not just the temperature anomalies, the warm anomalies, so they have the real and strong impact on the marine ecosystems, fishery, and also for the biodiversity. So here I show 2 groups of photos, which is the ecosystem before and after the marine heat wave events. So we can see marine heat wave can lead the widespread die-off of the kelp forest, and also it can lead the large scale of coral bleaching. And besides of this, so the marine heat wave is also threatens the economically important species like the lobster, like the crab. So the lobster are very sensitive to the water temperatures. So when the marine heat wave happens, the sea surface temperature it will become warmer, and the lobsters it may leave their habitat or it even just lost their lives. So marine heat waves do not just warm the ocean, so they can disrupt the ecosystem, damage the fisheries, and affect communities. So this is why they deserve our attention. So here I show the map of recent years marine heat wave events. We can see this event occurs across all ocean basins. And in recent decades, so the marine heat wave have become more frequent, more longer, and stronger. And this trend, it will keep accelerating with ongoing global warming. And this is where my research comes in. So my work will focus on understanding the key processes that shape the global marine heat waves. So today, I will start with the Pacific, highlight the climate mode like the Pacific Decadal Oscillation, and then we will look at the Atlantic, the very important ocean circulation, AMOC. And then, I will give a broader view of how ocean dynamics shape the global marine heat wave by comparing the dynamic ocean and the slab ocean. And so these three are all the internal processes in our climate. So while the external forcings like the greenhouse gas and anthropogenic aerosols also have the impact on the global marine heat waves. So this is my last part. Okay, so let's start from the Pacific. So marine heat wave. So Northeast Pacific has been a hotspot of the marine heat wave in recent years. So I think everyone heard about the very famous event named Bob, happens in 2014. As you can see here, so the large area of the ocean becomes unusually warm, and a similar condition is show up again in 2019. So these events are not just strong but also long-lasting, and it covers very large areas. So what causes the marine heat wave events repeat to happen in the Northeast Pacific? Our hypothesis is that in addition to the long-term global warming, the climate variability may also be very important. They may play as an amplifier or the modulator for the marine heat wave events, the warm extremes in this region. So in the Northeast Pacific, I think we think the key factor must be the Pacific Decadal Oscillation, the PDO. So PDO is a leading mode of the decadal sea surface temperature variability in the North Pacific, and it is characterized by the basin-wide warm and cool patterns like these two figures shows. And if we look at the PDO index, so here is the PDO index from the Heatwaves SST observations. So we can see both the 2014 and 2019 events happened during the positive phase of the PDO. So it brings us to the first question. So how exactly does the PDO, the positive phase, influence marine heat waves in this region? Can they promote the marine heat wave occurrence, or can they just increase their intensity or the frequency? To answer this question, so first we start from the OISST version 2.1 observations, and we use the daily SST output. So we choose the two different PDO positive period, which is 1982 to 1998 and 2013 to 2022. And also we have one negative PDO period, which is 1998 to 2013. And if we compare the marine heat wave performance between these two phases, two periods, here is the result. So in this figure, so from the top to the bottom, I show three different marine heat wave metrics: duration, frequency, and intensity. And from the left to the right, I show the negative PDO phase, positive PDO phase, and the difference. So we found that along the Northeast Pacific coast, so marine heat waves are longer in duration and become more frequent and have a stronger intensity during the positive PDO time period compared to a negative one. And this confirms the PDO influence marine heat wave in the Northeast Pacific. And a positive PDO phase, it acts like a switch that triggers the occurrence of the marine heat waves in this region. But here, so we still have a problem. The observations, so all of the observations, this is on top of an anthropogenic warming trend. So it makes tricky to separate the PDO effect very clearly from the long-term global warming. So because of this, we need the large ensemble simulations from the climate models to eliminate the background warming and to isolate the PDO effect. So here I use 5 different climate models from CMIP6, and it's under the historical and future forcing scenarios, which is SSP245. And in total, I have 174 ensemble members. So for each ensemble members, we calculate the PDO index. As you can see on the left, so the average across all members is as shown in the black thick line, so in the middle. And this black line stays nearly flat. So this means that by pulling all across many realizations, all ensemble members together, so the anthropogenic warming signal, we can just average out. And this allows us to classify individual ensemble members into the positive PDO and the negative PDO groups. So here we select 20 members for each phase during 2013 to 2022. And then so compare the difference in Marine heat wave between these two groups. Okay, here are our large ensemble results. So compared to the negative PDO phase, we can see that along the Northeast Pacific coast, Marine heat waves are significantly longer in duration, higher frequency, and stronger intensity during the positive PDO years. And these results are consistent with we just demonstrated by the observations. And the effect of the anthropogenic warming, so they also still included in the large ensemble result, but if we calculate the difference, so it will compensate, it will average out. And therefore, so this result can suggest that PDO has a moderating effect on Northeast Pacific marine heat wave in the last decades, more in a clear way or a clean way. So since the moderating effect of the PDO is most evident along the coastal region, so we next perform the probability density function analysis of the sea surface temperature in this coastal black box region. So on the top is our probability density function result. So in the middle, so is all members means, all ensembles mean, which we can see as a neutral position. And the grid curve shows a mean SST is about 15.4 degrees Celsius. When we just separate the ensemble members into positive and negative groups, so we can see a clear shift in the PDF distributions. So during negative PDO, the mean SST is about 0.8 degrees Celsius cooler, while in the positive PDO, so the mean SST is about 0.9 degrees Celsius warmer. And the PDF, the distribution, is skewed towards to the warm extremes. So this suggests that the background SST state is important for determining the likelihood of the warm extremes. But on the other hand, so the PDF not only tell us the information about the warm extremes. So if we look at the left tail, so we can see that the negative PDO also will increase the likelihood of the cold extremes. And but if we only look at the PDF alone cannot tell us how these SST differences evolve. So if we want to really understand the mechanism, so we still need to go beyond the statistics. So first, so we decide to look at the SST trend, the difference of the SST trend between the positive and the negative PDO groups. So the results show us a clear coastal warming signal in the Northeast Pacific coast during the positive PDO phase, with an anomalously warming rate about 0.6 to 2.3 degrees Celsius per decade. And our next question is, what physical processes drive this coastal warming under this positive phase? Here, so we identify two different key mechanisms. Yes, first one is anomalous. We have in the coast region, so we have the anomalous southeasterly wind along the coast, which can enhance the downward Ekman pumping. So the downward Ekman pumping will suppresses the upwelling of the cold water, and it will warm the surface. So second, another mechanism. So we look at the net surface heat fluxes. So more heat is entering in the ocean through the surface, mainly from the stronger downward radiation and also the reduced turbulent heat fluxes. And together of these two mechanisms, so explain why Northeast Pacific warms more strongly under a positive PDO and why we see longer and stronger marine heat wave in this region. So now, so we can wrap up the PDO part. So we found that the PDO acts as an important modulator that amplifies the impact of global warming on regional marine heat waves. And based both on the observations and the model simulations, so marine heat wave have become longer, stronger, and more frequent during the positive PDO times compared to the negative phase. And we found that so this is primarily linked to the mean state SST differences between the two phases, And also during the positive PDO, the coastal region, so it will experience the reduced cold upwelling and the enhanced of downward surface heat fluxes, and both of them favor the warm surface SST. And here we also do the quantification of the PDO effect on the marine heat wave relative to the background global warming. So our results show that the positive PDO, it can increase marine heat wave duration by about 43%, frequency by about 32%, and the intensity by about 10%. All of these are relative to background anthropogenic global warming. Okay, so then let's move to the Atlantic. So talk about the Atlantic, I think the most very important part is the AMOC, the Atlantic Meridional Overturning circulation. So AMOC plays very important role in redistributing heat and regulating the sea surface temperatures in the North Atlantic. So you can think of the AMOC as a conveyor belt. So it can move heat from the low to high latitude. So it transports warm water northward near the surface, and it will return cold water southward at the depth. But this circulation is not always stable, so it has this decadal variability. And as shown here, so both models and observations suggest that the AMOC is slowing down in response to the anthropogenic warming. And the climate projection indicates that so this weakening is likely to continue throughout the whole 21st century. And here is our question. So how will this weakening of the AMOC have the influence on the occurrence or the characteristics of the global marine heat waves? To address this question, so we still use both observations and the climate models. So here we use the OSST version 2.1, just like the first project, because this data is of good quality and high resolution, and has been widely used in recent years for the climate extreme studies. And for climate models here, so we designed two parallel simulations based on the CCSM4 climate model. So both of them have 5 ensemble members and based on the same scenarios, historical and RCP 8.5. So in the AMOC free runs, the blue curve showing here. So the model includes the natural weakening of the AMOC due to the climate change. Parallel to the AMOC free, so we conduct a sensitivity experiment. We call it AMOC fix. So in this experiment, the fresh water is extracted from this orange region, the North Atlantic deep water formation region. And we just separate this fresh water evenly to the other global other regions. And by doing that, so the AMOC strength can be maintained in a warming climate throughout the whole 21st century. And if we compare the marine wave behavior between these two simulations, so it can tell us and it can help us isolate the impact of the AMOC slowdown on the global marine heat waves. So first, we compare the models, AMOC-free model simulations with observations. So we want to make sure that our model can capture the main features of the marine heat wave behavior in the global ocean. So I think the model did a very good job. So compare with the observations it's on the right hand. So the model is on the left hand. The model simulates an overall longer duration of marine heat waves, but a little bit lower annual frequency and a little bit weaker intensity. So this slightly difference, it may come from the fact that the daily SST climatology in the observations, so it only have one realization. So it means that we have the internal variability, we have a lot of other effects. But for the model we have 5 different simulations. So and this model result, so it's average of these five ensemble members. So it can help us to minimize the impact of the climate variability and better express the daily SST climatology under the climate warming. So after make sure our models can do a good job, so we start to do the analysis of the marine heat wave behavior between AMOC fixed and AMOC free experiment. So here is our result for last 4 decades, 1981 to 2020. So we can see in the AMOC-free experiment. So during the last 40 years, we have long lifetime and strong intensity heatwave events occurred in the eastern tropical Pacific, and the average duration for this region is around 70 days. It's pretty longer. And we also found some short lifetime, but even strong intensity heatwave events that happens in the western boundary current extension region, like the crucial extension and the Gulf Stream extension. And if we compare the AMOC-free with the AMOC-fixed, so we can see a reduction in marine heatwave duration and frequency, especially in the North Atlantic. But if we look at in a global scale, so the changes in the marine heatwaves is generally insignificant. So we think this is maybe related to the relative small amplitude of the AMOC slowdown during the past 44 decades, like this figure shows that. So because of this, so we further investigate the impact of the AMOC on global marine heatwave in the future climate, so where we have much more stronger AMOC difference. So during the 2061 to 2100, the impact of the AMOC, weakened AMOC become more striking if we look at this column. So we can see a kind of bipolar seesaw pattern with more frequent marine heatwave events in the Southern Hemisphere, but fewer in the Northern Hemisphere. And if we look at by the end of the 21st century, so the Northern Hemisphere, south of Greenland, this region, it remains the most sensitive area for marine heatwave to be affected by the AMOC. And if the AMOC does not slow down throughout the whole century, so the North Atlantic warming hole region, it will reach a near permanent marine heatwave state. Yeah.
Can I ask a question about your the setup of this experiment AMOC fix?
Yeah.
So you keep hitting the North Atlantic with extra radiative forcing because it's RCP 8.5 forcing, right? But you prevent AMOC from slowing down. Are you concerned that you may overheat North Atlantic this way?
No. So all of these experiments, so we just use the similar forcing with the original simulation of the original historical simulation. Like we use RCP, same forcing for both simulations.
Right.
Yes. So what we do, we just control the freshwater flux.
Correct.
Yeah.
But you keep delivering heat by AMOC that is still strong.
Yes.
So that may overheat North Atlantic.
Yes. Yes. I can show you this figure. I can't. Yes. So this is our SST plot. So we can see if you look at the red column here. So first, both of them are the end of century. Yes, and the bottom one, this one is the difference between the AMOC fixed and AMOC free. Yes. We can see most of the signal, the sea temperature response is in the North Atlantic warming hole region.
Okay.
Yeah, for other regions, I think it's in the relative good magnitude.
Okay.
Yes.
Thank you. Appreciate it.
Sure. Okay. Here. Okay. So for this project, we also do the probability density function, but this time, so we choose 4 marine heatwave hotspots where always happen the heatwave events, like the coast of the California, the Gulf Stream region, the Mediterranean Sea, and also the crucial region. And also, so because we are looking at the AMOC effect, so most sensitive region is the North Atlantic warming hole. So we also do the analysis in this region. And the first and the third column is show us the PDF result in the last 4 decades. So which the AMOC difference is relatively smaller. So we can see in this period, so the mean state shift is not as strong as the end of century. So when the AMOC difference are much more stronger, yeah. And for each region, for this PDF, so each region, so we calculate the PDF for the daily SST anomaly, and this value is based at 0.1 degrees Celsius relative to the daily SST climatology during the reference time period for the AMOC-free simulation. Yeah, so each figures we use the climatology from the AMOC-free. And during the historical period, so we can see the effect is not very, it's quite limited. But if we move into the end of century, the future time periods, so the strong AMOC weakening, it will shift the PDF towards to the cooler anomalies, reducing the likelihood of the extreme warming events in this region. And this implies that the AMOC has weakened through the local mean SST cooling, reduce the likelihood of the market wave in the Northern Hemisphere. Yeah, just like Igor asked before. So in this project, so we found that the AMOC controls the weakened AMOC controls the surface marine heat waves mainly by changing the mean SST difference, the mean state of SST. Yes. And here is a short summary of the AMOC role in modulating marine heat waves. So yeah, as I said before, so in the last 4 decades, when the AMOC is the difference is relatively small, so the marine heat wave response to the AMOC slowdown is significant for the global view. But if we keep but the AMOC continuing slowdown, so this effect will become larger and significant. And it will cause a bipolar seesaw pattern, like we have the more marine heat waves in the Southern Hemisphere, but fewer in the Northern Hemisphere. Because of the AMOC slowdown, it will reduce the northward heat transport. And the AMOC slowdown, so by reducing northward heat transport, so the most important influence for that is the change. It can change the mean state SSTs in the North Atlantic. Okay, so I have already talked the PDO and also the AMOC. So they are quite different, but both of them, so they involve the ocean dynamic processes in their modulating role for the marine heat waves. And now, so I want to just step back and look at the bigger picture, how the ocean dynamics shapes the global marine heat waves, and also can they get some support for the marine heat waves decadal predictability or multi-year predictability. So if we want to test the ocean dynamics role in the global marine heat waves, so we use the CESM1 pre-industrial control simulations over the last 500 years. And we also use the daily SST output. So, and here, so I have 2 different model setup. The first, the dynamic ocean. So the dynamic ocean, it will include all of the ocean circulations, heat transport, like the current, advection, mixing, and all of them are represented in the model. But on the contrary, so for the slab ocean, only they have a fixed mixed layer depth, and the ocean dynamics are replaced by the prescribed heat fluxes. So ocean is not moved for this experiment. And by comparing these 2 setups, so we can see how much this ocean's own dynamics shapes the global marine heat waves. So here's our first result. And if you look at the difference between the dynamic and the slab ocean, so we can see that the ocean dynamics can significantly promote the marine heat wave intensity and duration in the Eastern Tropical Pacific. So we all know that the Eastern Tropical Pacific is highly related with the ENSO activity. So in this region, the duration and intensity of marine heat wave can increase by about 45% and 47% in dynamic ocean compared to the slab ocean. And when we look at the NINOS 3-4 SST variance and the ENSO power spectrum, so they also much stronger in the dynamic ocean compared to the slab ocean. So that's because the dynamic ocean captures the coupling between the tropical ocean and the atmosphere, and also it revolves the processes like the ocean heat transport, the vertical mixing, and all these processes help to sustain the ENSO-related SST anomalies. But on the other hand, so the slab ocean, they cannot do that. So it basically relies on the local surface heat fluxes, the atmosphere feedbacks, and also the ocean heat capacity. And our stories doesn't stop in the tropics. If we look at the mid and high latitude, so we also see a big effect of the ocean dynamics. So here, so the dynamic ocean tends to produce more frequent but shorter marine heat waves, unlike the clear ENSO mechanism in the tropics. So this region is much more complicated. So because we want to dig deeper, we turn to a regional mixed layer heat budget analysis. So here we focus on 4 hotspots: the Needle 3-4 region, the Mediterranean Sea, the Gulf of Alaska, and also the Gulf Stream. And for each region, so we line up the heat budget around the peak of marine heat waves. So that is month 0. And then, so we look 6 months before and 6 months after. So this way we can see how the different heat budget terms evolve over the whole marine heat wave life cycle. So first, look at the Needle 3-4 region. In this region, so the blue line here is the temperature tendency of the dynamic ocean, and the red line is the temperature tendency of slab ocean. And we have another 3-4 dotted lines. So all of these are the 4 different terms of the heat budget in the dynamic ocean. So in the Needle 3-4 region, we can see that the rapid heat buildup before about 1 to 2 months before the peak in the dynamic ocean, the blue line here. But if you look at the slab ocean, the signal are only about a quarter as strong as the dynamic ocean. So in dynamic ocean, both surface heat fluxes and the horizontal diffusion keep adding heat throughout the event. But at the same time, so advection and the vertical mixing, it will act in the opposite way, so providing cooling. And the balance between the positive and the negative terms is what controls the full life cycle of the marine heat waves in this region. And next, we'll look at the Mediterranean Sea and the Gulf of Alaska. So these 2 regions have similar patterns of the heat budget terms, and both of these regions are have happened more than 2 times of the marine heat wave, very strong marine heat wave events in the past few decades. So marine heat waves are weaker in the dynamic ocean in these regions. And also the slab simulation, it shows strong warming trend by the surface heat fluxes, but in the dynamic ocean we can see the warming effect is from that surface heat fluxes is relatively weaker, and the vertical mixing, it will help to buffer the heat anomalies, and it will cause the reducing SST extremes. And last one, so the west is, I think this is a representative of the western boundary current region, which is the Gulf Stream. So the Gulf Stream is different, and we have here, so the persistent negative surface heat flux, the blue line here, and it's basically continuously heat loss to the atmosphere, and it's basically continuously it helps to suppresses the marine heat wave intensity. And but at the same time, so we still have the advection and the diffusion bring some heat into the ocean, but it cannot accumulate effectively. So the extremes are dampened in the dynamic ocean compared to the slab one. So all this together, so this particle analysis shows that ocean dynamics can either amplify or reduce the marine heat waves, depending on the regions and the local processes at play. So next, so we move to the predictability part. So our heat budget analysis highlights the importance of ocean dynamics in regulating marine heat wave evolution, and it further motivates us to ask whether this difference between dynamic and the slab ocean is also come out as a long-term predictable signals within the climate system. So to test this, here we use the spatial patterns of the potential predictability variance friction. So we call it the PPVF. So this PPVF can measure how much of the variability comes from the lower frequency timescales. And what we found is that, so if you look at these figures, the first red column is dynamic ocean, red is the slab ocean, And from top to the bottom, I choose 5 years, 10 years, and 25 years running mean. Yeah. And here our results shows that the dynamic ocean, so regions like the North Atlantic, Southern Ocean, and Western North Pacific, it shows larger potential predictability. While in the slab ocean, so we have higher potential predictability in the equatorial Pacific. But the PPVF, it can only tell us the signal where the potential high predictability happens. And the next step is to ask, so how long can we potential predict marine heat waves in these regions, and what processes give rise to the predictability skills? So to address this, so we use the average predictability times APT method. So this method quantifies temporal range of the marine heat wave predictability, and given the previous results showing the PPVF, so first we choose the North Atlantic as our target region for the future investigation. And here, so based on the APT methods analysis, so we find that the marine heat wave frequency in dynamic ocean, it can be predicted up to 5 years in advance, while in the slab ocean, the red line here, so it's only about 2.5 years in advance. And we also look at the spatial pattern of the APT1. So in the dynamic ocean, the leading predictable mode, APT1, shows like a dipole pattern between the Labrador Sea and the Gulf Stream region. So this pattern is similar like to the well-known AMOC fingerprint. And it's indicating that the APT1 mode is potentially linked to the lower frequency variability of the AMOC. So we further test the Lig-lag correlation between the AMOC stream function and the APT1, the PC type series, to confirm that the AMOC's role in marine heat wave predictability. So our result shows here, it shows that the AMOC stream function, it shows a significant negative correlation with the APT1 index when the AMOC lead by 6 years. So in other words, so it takes roughly 6 years for a weakened AMOC to leave its imprint on the North Atlantic SSTs. So this delayed response highlights the memory carried by the AMOC and its important role in shaping the multi-year predictability of marine heat waves in the North Atlantic. And the AMOC-driven long-lasting sea surface temperature anomaly patterns is act like a preconditional background state. So they substantially modify the probability of the marine heat wave occurrence in the specific region, and thereby so providing a predictable foundation for marine heat waves or other extremes over the following years. But on the other hand, if you look at the slab ocean, so slab ocean lacks of the AMOC-driven current or the deep ocean heat exchange processes. So the SST anomaly here are more localized, and its predictability is much more shorter than the dynamic ocean. Okay, so we can here I can wrap up the this section, and here so I want to highlight 3 takeaways. First, the ocean dynamics is really matter, and they can make the marine heat wave stronger, longer, and also on the other hand, in some regions, so they can make the marine heat wave become more frequent, but a little bit shorter. And especially, so we look at the marine heat wave in the eastern tropical Pacific, where it is closely tied to the extreme El Nino, the extreme ENSO events. And second, so the underlying processes are important. The vertical mixing and the horizontal heat transport, they strongly shape how the heat build up. And so the intensity and the life cycle of the marine heat waves looks very different in a fully coupled ocean compared to a slab ocean. And last one, so the North Atlantic is a special region we choose, and thanks to the AMOC and the long-term variability, so we found the robust multi-year predictability scale of marine heat waves frequency, duration, and the intensity in this region. So this really emphasizes that the ocean dynamics, so they are not just so they are very important for predicting future extremes and planning the adaptation strategies. And yeah, I think still have some time, so I will introduce a little about the external forcing impact on the global marine heat waves. So we all know that greenhouse gas will warm the Earth's temperature and the aerosols, so it will offset the greenhouse gas warming. But how do this kind of the warm and cooling effect of the external forcing affect the marine heat waves? So I think we can have some hypothesis in mind, like the greenhouse gas, it will cause the mean state of SST become warmer, and the aerosol, so it will cooling the mean state of SST. So like we did before. So by changing the mean SST, greenhouse gas and aerosol, so it can change the likelihood of the climate extremes. But in this project, we want to find another way. So in addition to the mean state shift, so can these forcings also change the shape of the SST probability distribution? Like we have larger cortices, we have smaller cortices, and the shape of the probability distribution also will have influence on the climate extremes, both for the warm and the cold. So here we also use the OSST to test our model. And for the model simulations here, we choose two different simulations: the historical simulations, which has all of the forcings, and the single forcing simulations. So which is where we isolate the effect of the either greenhouse gases or the anthropogenic aerosols. And here, so importantly, so for each simulation, we recalculate the daily climatology. So in this way, so we can remove the impact of the mean state SST differences, and can directly focus on how the greenhouse gas and aerosol separately modulate the marine heat wave by changing the PDF shape. So this is an overview of the greenhouse gas effect. So we can see the greenhouse gas alone, so it will increase the marine heat wave duration, frequency, and also intensity in most regions of the global ocean. Well, yes, and the aerosol, it will have a cooling effect for all marine heat wave metrics in global ocean. And then, so look at our probability density function analysis. So here, so the gray line in the middle is our historical simulation, and compared to the historical one, the green line, so we can see greenhouse gas only, it shows smaller cortices. And it can foster the occurrence of the climate extremes. Instead of that, so the aerosol only scenario, so it has a larger cortices, which it will mitigate the occurrence of the climate extremes. And throughout our quantitative analysis, so we found that based on the 99th percentile of the sea surface temperature anomaly, the cortices difference in the historical greenhouse gas and the aerosol experiment, it can result in a increase about 0.25 degrees Celsius, while a decrease of 0.35 degrees Celsius. And this magnitude is relative, is comparable to that changes by the mean state shift. So that means that the cortices change is also very important, not only the mean state shift by the external forcings. Okay, so here I will give a short summary of this talk. So in this talk, so we have looked at how both external forcing and internal climate variability shapes the marine heat waves. So we start from Pacific, look at very important climate mode, the PDO. And we found that the positive phase of PDO, so it will promote the warm extreme happens in the Northeast Pacific coast region by control the upwelling and the net surface heat fluxes. And second, so we look at in the Atlantic, the AMOC effect. So we found that the weakened AMOC, so it will reduce the northward heat transport, which can reduce the likelihood of the marine heat wave in the Northern Hemisphere. But it's like a bipolar seasonal pattern, so it will cause more marine heat wave happens in the Southern Hemisphere. And third one, so we look at the ocean dynamics, and we found that different regions, we need to do the case study or the regional studies because of the different local processes, and both of the advection, vertical mixing, and also the atmosphere feedback. So all of them will have the effect on the Marine wave evolution or the life cycle. And here we also found that the AMOC, the decadal variability of AMOC, so it will help to enhance the predictability of marine heat wave in the North Atlantic. And the last one, so we look at the external forcing effect. So we choose the greenhouse gas and aerosols. As we all know that the greenhouse gas will increase the likelihood of marine heat waves, while aerosols, it will reduce the likelihood of marine heat waves. But in this project, so we change into the different ways. We haven't looked at the mid-state shift, but we look at how the external forcings changes the PDF distributions, the shape of distributions, like they school it or make it thinner. So in this way, so we found that these currency changes cause the influence on the marine heat waves is comparable with the mid-state shift. And all this together, so these findings show that both external forcings and internal variability and ocean dynamics, they all fundamentally control the evolution of the marine heat wave, and also can give some hints for the predictability skills. And this has an important implication for anticipating future climatic extremes and guiding the adaptation strategies for marine ecosystems or the coastal communities. And we think that our research will not only stop in the marine heat wave, this one kind of extremes. We still need to care about the compound extremes, like how marine heat wave will have the interaction with the tropical cyclones or the land heat waves. So all of this to find out the mechanism behind this compound events, so it will give us more confidence or more hints for the marine ecosystem protect and the coastal communities. Yes. And I want to acknowledge all of my collaborators from the UC Riverside, from GFDL, and also NOAA, and from Australia. So yeah, thanks for them. So we can continue to work on this project for 5 years. And thanks you all for today's attention. And I'm happy with any questions.
Questions for Xianglin, please?
I have a question. Thank you for the wonderful. Thank you for the presentation, Xianglin. I had a question about the Gulf Stream. You said it's shifting northward as the AMOC weakens. Did you have a figure where you explored that?
Yeah. So I haven't put that figure here. So I think so we compared the Gulf Stream, I think the current axis between the AMOC-free and AMOC-fixed experiment. And we see that if we have the AMOC-free experiment, so the Gulf Stream, the current axis, it will become a little bit northward. Yeah, cause and in the AMOC, in the AMOC-free, I think when we have a strong AMOC, so the Gulf Stream will become northward, a little bit northward. When the AMOC weakens, so the Gulf Stream is a little bit southward. Yeah.
Okay, so you mean it's tilting?
A little bit.
Okay, that makes sense. Thank you.
Hi, thank you for the talk, that was nice. In your third chapter, you compared two models, the slab and the ocean dynamics models. Were either of those, or both, a coupled air-sea model?
Yes, they are both fully coupled climate models. The only difference is the slab ocean don't have the ocean dynamics. Yeah, it's just use the prescribed surface heat fluxes to pretend like the ocean response. Yeah. And it has the fixed mixed layer depths.
Okay. Thank you.
Philip? Yeah, I just want to clarify that for your slab ocean model, there's no like current forcing at all in the model, just the heat fluxes?
Yeah, specific heat
Alright.
fluxes.
Thank you.
And I can show the heat budget equation for the, yes, for the slack ocean. So we only have the heat fluxes contribute to the heat. But for the dynamic ocean, so we have the 4 terms, yes.
Yeah, thank you for the presentation. I have a question about your AMOC-free experiment. And also in the very first few slides that you presented, you showed the definition of your marine heat waves, the baseline, some climatological seasonal cycle. And then I'm wondering, when you have your AMOC-free states, or the AMOC weakening state, that changes also your mean states, and it changes the meridional heat transport. So do you adjust your definitions for duration, intensity, and frequency of the meridional heat waves when you have a different mean state?
No, we haven't changed the definition. So I think the most important for detect marine heat wave is which climatology you choose. Yes. So here, so I think I forgot to mention that. So for each time period, so we use the climatologies from the AMOC-free simulation. Yeah, we use this for 1981 to 2020. So for the AMOC-free experiment, when we detect marine heat waves, we use the climatology from itself. Well, in the AMOC-fixed experiment, we still use the climatology from the AMOC-free. Yeah, that can help us do a little bit like the clean way to isolate the AMOC impact. Yes.
Okay, thank you.
I have another question about the coupling of your models. Do you include momentum flux at all?
Yes, for fully coupled climate model, I think so.
Okay, in both?
Yes, in both.
Okay, thanks.
Can I ask you a question about the same part of the study when you
Yeah.
compare the dynamics and Slav ocean? So the dynamical model does not include mesoscale, of course, right? The resolution is I'm assuming it's low, right? Do you anticipate importance of mesoscale currents and sharper Gulf Stream fronts and other mesoscale features?
Yes, actually the model I use is 1 degree.
1 degree, yeah.
Yeah, so it can show some mesoscale signal here. Yeah, but we also try the 0.25 degree and also shorter left time, but for 0.1 degree.
Okay.
Yeah, detection, but it takes more time
Of course.
to run. Yeah, and of course, yes, mesoscale processes are very important in the western boundary current region, like the Gulf Stream, and also the Gulf return current region. Yeah, and we try to do the quantitative analysis, like compare so how much this eddy or the mesoscale effect compared to the mean state effect. Yes, and I can see. I think I recall that our results show that in the Gulf return current region, so the moment the mesoscale effect is as strong as the mean state.
Mm-hmm.
Yeah, and we can see a little bit signal in this figure. I think, yeah, we have relatively strong signal along just along the western boundary extension region. Yes.
Thank you. Other questions for Xianglin? If not, let's thank you again.